Okay, so the topic of my presentation will be fragmentation of tropical forest, and then there's a question of forgotten process in the global carbon cycle. To start, what do we know about the global forest? Here's a map which was compiled in the year 2000 by the UNEP, and which shows in different colors the different forests of the world. In total, we have around 30% of the area covered with forests. So if you calculate the area per person, you get 0.5 hectare forest per person on the world. And we distinguish three main different types. So we have, with the largest amount, tropical forest, then we have the boreal forest, and then we have also temperate forest. And there's also a lot of biodiversity covered in these forests, and this is quite difficult to estimate. So if you focus only on the tree species, then one published estimate is that we have in total around 50,000 tree species in the forests of the world. So what do we know on the role of forests in the global carbon cycle? So this is a figure which shows the main pool as far as we know of the global carbon cycle. We have in total numbers 800 gigatons carbons in the atmosphere. So these are the latest numbers published last year. So this is related to this famous ppm. So this corresponds to 400 ppm. And we have in absolute numbers an increase of 4 gigaton carbon per year. And then, we try to estimate also the carbon content of the vegetation, but this is quite difficult. So here in this graphic, so this is the graphic from the paper of Grace. The estimate was for above ground carbon 600 gigatons, but in the new IPCC report we find a large range, and if you look at the reference in this report, it's a reference to the IPCC report 10 years ago, before, a paper by Prentice. So this shows again that we don't know much about really the carbon amount stored in the vegetation. But vegetation is quite important because the order of the amount which we estimate for the carbon in the vegetation is the same order as the atmosphere. So if we have change in the carbon content of the vegetation, and this will be emitted in the atmosphere, this will have strong impacts on the carbon content of the atmosphere. So there have been a lot of attempts to quantify the flows between vegetation and atmosphere. And so there's one flow, this is called the terrestrial uptake. So it's currently estimated around 2 or 3 gigaton carbon per year. And there's this also well discussed flow due to deforestation. So we have deforestation of forests, and the current estimate is around 1 gigaton carbon per year. So this is related to a new publication of Houghton in the year 2012. So this deforestation flow is now the topic of my presentation, and to give you a more clear picture what means deforestation. So this is a picture from the Amazon. You see here the clear-cut areas, and we see fragmented forests. And if you have a closer look, so again, we have here the clear-cut area, and we have core area of forest, and then, and that's now my topic, we have edge area of the forest. And the focus of my presentation will really be on this edge area, not on the deforested area, but on the edge area of the forest. So, we have some work from people from the ecological community on this edge area of forests, work by Lawrence, for example, and we know that fragmentation changed the dynamics of forests in the edge area. So we get a changed climate in this edge area. There are different wind conditions, there are different temperatures, and in the end we got higher tree mortality, and we lost biomass in these edge areas. And there have been very prominent papers on this in Nature and Science, and in the end we also get a change in species composition, tree species composition in these edge areas. And there have been also discussion what is the size of the edge area, and there are different estimates, and it depends also from the question, so it ranges between 100 and 300 meters. And we have also, that's fantastic for this question, we have also large-scale experiments. So this is a famous experiment from Lawrence in the Amazon. So here's a picture of this experiment. We have some new experiments in Borneo, done by the Imperial College of US, and then they have very classical experiments done by Robinson and Holt in Kansas in the United States. And to give you an impression what we can get out of these experiments, so here again it's a discussion how large or what is the size of the edge area, and it depends a little bit what you analyze. So you have your different foci of research, so you can look at the humidity, for example, so you will result at a distance of 100 meters, and you can look, for example, at elevated tree mortality, and so you get another size for the edge area. So if you know that in the edge of these tropical forests there is a higher mortality, it's also interesting to quantify the loss of biomass over time, and this can be done by forest models, and we have done this in my group. So we are working for more than 20 years on local vegetation models for tropical forests, and this is one of the results of these analyses. So we plotted here in equilibrium the biomass, above ground biomass, which we get in the forest for different fragment size. So the fragment size are in hectares. So this is a fragment of 10 hectares, this is a fragment of 40 hectares, for example. And the upper line indicates the situation without fragmentation, so this is for forest near Sao Paulo, and the lower line is the equilibrium state or mature state of a fragment. And you see, if you have a very small fragment, you get a quite high loss of above ground biomass, and this you can simulate with forest models. And the next point is if you add, and we have also done this, but this is not included in the study I presented here, if we add now additional disturbances to the dynamics of a forest, like logging events or small fire events, then you get even higher losses of carbon in the fragment edge area. So why I present now this talk here on this nice workshop. So we try to relate now our local results with remote sensing data, and we looked for maps on vegetation type. So we looked on satellites with optical sensors, and there we took the results of the Envisat MERIS sensor. So this is a satellite which was launched 2002, and which covers a certain spectral range, and you get measurements every 3 years at a spatial resolution of 300 meters. And from this, people in Belgium and in Italy from the ESA, they developed the globe cover map, and there will be also a presentation directly from people which have developed this map on this conference. So this globe cover map has a quite high resolution. There are similar products also from the MODIS side, but they have a little bit lower resolution. So in the end, so this is this globe cover map from 2009. So you end up with 22 vegetation type. And now we did a very, very simple thing. So we are just interested in tropical forest area and non-tropical forest area. So we took 2 colors and classified reclassified the vegetation type, and in detail, it's a little bit more complex because we distinguish for the no tropical forest in 2 natural vegetation types and non-natural vegetation type. But I will come back later to this point. So, and then you can do a fragment counting. So we applied certain software, and in total we get in the tropics around 2 million forest fragments. The mean size of a fragment is 550 hectares. We have many, many small fragments and only a few large ones. And to give you some more impressions, so we have 3 very, very large fragments, which contributes to 63% of the total forest area in the tropics. So, and these are located in the Amazon River basin, in the Congo, and on Borneo Island. And here you have these frequency distribution for the different fragment sizes. So we plot here the number of fragments for the different continents over the fragment size, and the fragment size is indicated in hectare. And you see we get, so this is a double fragment plot, so we get more or less a power law, and we get, and that's the first interesting thing from my side, we get a power law at every continent, and it looks quite similar. And if you, for example, now are interested in the number, how many fragments are smaller than 50 hectares, you can calculate this from this distribution, and you will end up with the number of 80%. So we have a very, very large number of small fragments. But keep in mind, we have also a certain resolution limit in this analysis. I will come back later to this. So now we can get on. So if you assume a certain forest edge area of 100 meters, we can now estimate from this fragment analysis the total edge area. So it corresponds to 10% of the total forest area. And then we distinguish into border areas which shows a natural vegetation type, or which is a vegetation type which is created by humans. And then we end up with an edge, and this we call the anthropogenic edge area, and we end up in total with an edge area of 93 billion hectares. No, this is wrong. Million hectares, sorry, and this is 8% of the total forest area. And here you see some graphics, how it's distributed between the different continents. So we have a large amount, most parts of tropical forests are located in America, and there 6%, so this number indicates the fraction of the anthropogenic edge area, so 6% is border area, in Africa 7%, and in Asia and Australia it's much higher, so the fragmentation is much stronger in Asia, where we have already 20% of the total forest area is located in 100 meters of the forest edge. So these are really high numbers. And now you can combine this with information about the above-ground carbon content of the forest. So we have typical estimates for the above-ground carbon content of tropical forests in different regions of the world, as for example with palm paper. And from this, combining this with the forest area in the different regions, we can calculate the total amount of above-ground carbon stored in these forests, and we end up with around 180 gigaton carbon. And this is quite similar to the estimates also put by other people, for example, Joe Wright from Smithsonian Institute published similar estimate 2010. And then we can look how many carbon is now in the edge area. If you assume an edge depth of 100 meters, so it's 50 gigatons. And then we have to know how much of this carbon will get lost through the fragmentation process. So it's around between 0.5 and 0.6 the fraction. And this is related to modeling studies, but also to fragmentation experiments. And we end up with carbon losses in the edge area of tropical forest in the order of 8 gigaton carbon. And you can also now modify a little bit the assumptions, so you can change, for example, the amount of carbon losses, or you can modify also, you can even assume a larger sizes of the area, and then end up even with higher values for the loss of carbon. And again, if you look now at the distribution at the different continents, so most of this carbon is occur in America. The smallest amount is related to Africa, and we have all quite high losses in Asia, Australia, and this is again, so this graphic I have shown already, this is related to the high amount edge area in Asia and Australia. And now, you can go on and you can derive from, it's not very well represented here on the monitor, you can calculate a map in which show for each part of the world what will be the losses of carbon due to this area
of forests, and here we have legends. We recalculated the carbon losses in tons per hectare. We have different colors, and we get very high losses if you see the red colors. And the red colors you find normally for individuals which have very, very small fragments. There you have a lot of border area, and so you get high losses. So this is, for example, a typical situation of Brasilia, and so you can compare different regions of the world. Again, this is done under certain assumptions for the size of the edge area and losses. And the last now, it's interesting to bring in the time. So to quantify per year how much additional loss will cost this per year. And you can do this now with relations, also with the local vegetation models, to quantify the time frame for carbon losses for the edge area, and you get values between 10 and 50 years, so it doesn't take. But there's also some uncertainty because we don't really know the history of forest fragments. There's also done work by Bob on this question, very interesting work from my side. And you assume now that these losses will be emitted over a period of 30 years, you end up with additional carbon losses in the order of 0.25 gigaton carbon per year. And now this number you can compare with the number I put to you at the beginning. So with the number of deforestation, so it was calculated by Houghton, so it was 1.1 gigaton. So you see that with 0.2.5, this 0.25 is quite high. So it's already 20% of the yearly carbon due to deforestation. And if you would assume a larger size of the area, it would even be higher. So to conclude, we try to analyze the fragmentation of tropical forest using the globe cover map produced by ESA. So it's a map with a resolution of 300 meters. The first result has been that 10% of tropical forest area lies within 100 meters of the forest edge. Then we also derived these fragment size distributions. They follow a power law at all continents. And due to the higher mobility of trees in the edge area, we get additional carbons. And if you try to quantify, the order of 0.25 gigatons per year, and this is quite a large number. So our conclusion is fragmentation of tropical forest substantially contributes to carbon losses. Now this forest is not included in global carbon balance. Thank you very much.
Time for a quick question. Hi. To what extent do your estimates take account of soil as well as vegetation?
No, there's no emission of soil, it's above ground biomass.
So, could you perhaps speculate how much change your estimate, including soil, might take? I would expect maybe to see an increase in soils when you first use the vegetation plants, and then over a long time you would start to get an emission because you've reduced your inputs, and that could maybe quite substantially change the estimate. It'd be an additional contribution, but I think it's not because the elevated mortality area is not very high. You cannot compare it with the logging disturbance. So it's well known the logging land in the tropical forest, then there are also strong impacts on the carbon in the soil. But this is really a low intensity disturbance. That's the interesting thing. It's very difficult to measure it. It's very hard to measure it directly with remote sensing. Also trying this. So to use actually remote sensing information to detect it. So we had to look at this, but assume it's a smaller part.